Hello everyone, welcome back to my YouTube channel. Today we're going to do waves, exam style questions. Sorry I've been posting recently. Been getting pretty busy. But yeah, let's go ahead and try these problems. If you look at it, it's 6 for 7. 6, 7. Anyway, let's go on to the question. Alright, so the first one says, we have a string, a stationary wave, on a string that has two instances of maximum vertical displacement. The frequency of the wave is 12 hertz, right? I'll probably just highlight it. A stationary wave on a string. And then we're asking for the speed of the wave, which is basically just velocity, right? So this is kind of like a formula question. They're just testing if you know the formula or not, and the formula is simply just velocity is multiplied by the frequency multiplied by the wavelength. This is lambda, which is used to represent wavelength. So first things first, we gotta make sure that our units are correct. So this seems right, but this seems a little off. So it's going to be velocity is equal to frequency, 12 hertz, which is seconds negative 1, multiplied by the wavelength. And the wavelength is from here to here, right? Just here to here. So it's 2/3 times 90, which is going to be 60 centimeters. Or 0.6 centimeters. If you do a calculator on that, you should get 7.2 meters per second. A loudspeaker emitting a sound of frequency F is placed on an open end of a pipe of length L, which is closed at one end, and then a standing wave is set up in the pipe. A series of pipes are then set up with either one or two loudspeakers of frequency F. The pairs of loudspeakers vibrate in phase with each other, and they're asking which pipe contains a standing wave. So first thing that we should know about standing waves, especially like in a tube, AICE loves testing these questions. So one thing that you should know is that that was bad. Actually, I'll start from this end. Basically, the first thing you should know is that on one side, on the closed end, it'll always end in a node if it's a standing wave. So we can just do this, and then it'll also end on a node as well. So this is essentially what a standing wave is, and if you've seen like the experiment, I'll probably post a link later. It'll make a louder sound at certain frequencies. So we're trying to emulate this type of pattern in our 4 choices down here, basically. So which of these can contain a standing wave? Unfortunately for the first one, since it's an open-ended wave, I'm pretty sure it's open on 2 ends. I'm pretty sure that the main way this one works is that there's always going to be 2 antinodes. Essentially like the peaks, right? So this will always be an antinode, this side will always be an antinode, so this is not a correct answer. For B, I think you can kind of draw the same thing as before. But the fact is that this is essentially a open-ended tube on both ends. So basically what this means is that it's going to be an antinode and antinode, despite the fact that there are 2 nodes. So this is also not going to be a reason why. And then also for C, we're just going to double the length. So that means that we're just going to have another period, right? So if we draw it, that's 1, 2, something like that. Sorry, I'm not used to drawing too much waves. It's not supposed to be concave up. Okay. So it's 2 lengths. So this is 1 length. This is another length. And then for D, it's going to be the same issue, where this is an antinode. God, I can't draw waves. So it's going to be an antinode versus antinode, kind of. So this is not going to be right. So A, B, and D are all wrong, and then thus we're left with our answer C. In a double slit experiment, the distance between the fringes on a screen was too small to measure. What would increase the distance between the fringes? So okay, a double slit, I'm pretty sure you have a wall, right? And then you have two slits, so it diffracts like this, kind of. When you have a source, and then you have kind of just fringes on like a back wall, kind of. And it gives you the distance. This is not to scale, but essentially it's more compact here. I'm pretty sure. Yeah, it's definitely more compact here. So like the fringes distance is more compact here, while it's larger on the ends, because it's like farther away, right? And the equation for double slit is just going to be AX over D. The way I remember it is this is AX. And then this is D. No, this is X, and then the bottom here is D. So it's pretty self-explanatory. The way I memorize it is like, you know, A on this side times X on this side divided by D, all over D basically. That's how I memorize the equation. I'm pretty sure this is the, like, yeah. And this is equal to some constant basically. This is equal to wavelength, I think, right? It's like, I forgot, to be honest. But it should be equal to a constant. And basically, if we want to increase the distance between the fringes, which is X, we want to say that A is inversely proportional to 1 over X, right? So let's decrease the distance between the slits to increase the distance between the fringes. And that's going to be C, I think, yeah. Okay, let's do some analysis on the answer choices. So increasing the distance between the light source and the slits. So if we increase the distance here, our denominator gets bigger, and thus our constant will get smaller. Yeah. Okay, so our distance becomes larger, right? And thus in response, this should also increase. But then we're also increasing A, so that means we have to decrease X basically. So A is not right. So increasing the distance between the slits and the screen. I think this is the same thing as A, right? Between the light source and the slits in the screen. I think it's the same issue, honestly. Let me know what you think. But I think that's how you justify. And then for D, increasing the frequency of the light source. Okay, so it is like frequency. So if we increase the overall product, it doesn't necessarily, if we increase the frequency, it doesn't necessarily affect the distance between the fringes, I think. It just increases the magnitude of like how dark it can be, essentially. But yeah. All right, so for the next question, what is not an essential condition for an observable interference pattern to occur between waves from two sources? Okay, so A, the frequencies of two sources must be equal. B, the sources must be coherent. And C, the sources must emit waves of equal amplitude. D, the waves from the two sources must overlap. Okay, so if we have like two waves, for example, let's say this, and also this, we can say they generally have an interference pattern, right? Observable interference pattern. It's just going to be a larger example, right? This is like the net wave, right? Essentially for these things to occur, it has to be coherent. Which is B, so it can't be B, which means that they have like they're identical waves kind of with same phase difference. So they have to match up on the waves. Otherwise they're gonna be like wonky. They're gonna be all over the place, right? So in this case, I'm pretty sure A also has to be eliminated because based on the phase difference, they have to match phases, right? So they also have to have the same frequency so that they meet on the same nodes and antinodes, right? And then for D, the waves of the two sources must overlap. If they don't overlap, how are we supposed to observe them, for example, right? So it can't be D, and thus our last answer is just going to be C. Source S emits microwaves with a constant amplitude. The microwaves hit a metal screen P and are reflected. A stationary wave is formed from S and P. The wavelength of the microwaves is much smaller than the distance between S and P. The detector Q is moved at a slow, constant speed. From S to P, what happens to the amplitude of the signal detected by Q? All right, so let's actually draw the thing. Thingamabobber. Actually, I'm gonna do pink and blue. Okay. So we know it's a standing wave, right? So it's gonna be from node to node. Now if we draw the wave, oh god, that's not equal amplitude. Just assume it's equal amplitude across. So if we move Q back and forth, basically, we can see that it actually goes up and down just like a wave. So it's just gonna be B, where it increases and decreases regularly. This should pop out at you. This just means it's based on the frequency, right? So this is after a certain amount of time. A pattern of waves, it was observed without being able to view the source of the waves. The pattern is represented by the diagram. Okay, so first off, we have a region of minimum intensity and a region of maximum intensity, and this should immediately snap you back to diffraction, right? And if we look at here, we have coherence, diffraction, interference. So it's definitely going to be diffraction. So we can remove A and D. And now we have to define if these are interfered. So we can see that this is generally like one wave, right? So I would say it's like an interference. These two waves are interfered to create like a bigger net wave, right? So I would say it would be B instead of just diffraction only. Which electromagnetic wave would cause the most significant diffraction effects for an atomic lattice spacing around 10 to the negative 10 millimeters? Yeah, meters, sorry. Okay, so I think that we have to find a wave that is smaller or much smaller than this, right? So the way I try to remember this, wait. All right, which electromagnetic wave would cause the most significant diffraction effect for an atomic lattice of spacing around 10 to the negative 10 meters? So if we're gonna create a diffraction effect, we want to make basically choose a wave that is similar to this wavelength. I think it's because that the slit, right? If you have a slit and then you put in a smaller wave, right? It'll diffract through, it'll actually go through, right? Because the diffraction is like, if you have multiple slits, right? If you put in a wave that is too big, everything is just gonna like not go through, right? So you wanna make a smaller wave, I'm pretty sure. So if we look at these waves, the way I like to do it is just start from the visible light spectrum. Sorry, which is around like 400 to 700 nanometers, right? Which is simply 4 times 10 to the second times 10 to the negative 9 meters, right? Which is around 4 times 10 to the negative 7. And then if we go above the visibility line, we have like infrared, etc. So we can say that A and B are automatically eliminated. UV is only slightly, so I guess it's not strong enough. But then we have X-ray, which is more believable. I'm pretty sure gamma rays are like 10 to the negative 10 to like 10 to the negative 12. I'm pretty sure, but it's somewhere around that, right? All right, wave generators at point X and Y produce water waves. I'm trying to zoom this in. At the same length, at point Z, the waves from X have the same amplitude as the waves from Y. Distance XD and YZ are as shown. When the wave generators operate in phase, the amplitude of oscillation at Z is 0, which could be the wavelength of these waves. Okay, so if we're going to have the amplitude is equal to 0, that means that if we have two waves, for example, and let's say they're the same waves, right? Can I copy this? Can. How do I paste it? Paste. Oh, there we go. Right, we have this, right? This is it when it's in phase, right? But if we shift it like this, right? We can see that at this point here, our net amplitude is equal to 0. Right? So that means that the difference in wavelength is around 1/2 wavelength is around 10, right? And then we can increase this for the period, I'm pretty sure. So if we do 3/2 lambda equals 10, 5/2 lambda is equal to 10, and then we gotta find the lambda where like the wavelength is an integer, because the answer choice is an integer. So if we do this one, we get lambda is equal to 20. It's not good. If we do this one, lambda is equal to 2/10, 6.67. Sorry, I got too excited. And then lambda here is equal to 4. Thus, the only viable answer is going to be C here. State two differences between progressive waves and stationary waves. First off, stationary waves don't move, hence stationary. Stationary waves don't transfer energy. Yeah. I think those are the most obvious ones, but I'm pretty sure there are more conditions to this. I don't know if this is actually sufficient. But essentially, progressive waves are just the opposite of this, right? Progressive waves are opposite, and same here. They're just the opposite of the definition I gave, right? All right, so for the next one, remember that we're describing how stationary waves are formed, and the way stationary waves are formed is that our waves are actually coherent. Let's look at our previous question here. The waves must overlap, and the frequencies are equal, right? All right, so next problem. A source S of microwaves is placed in front of a metal detector as shown in figure 6.1. Let me zoom this out. a microwave detector D is placed between D, R, and S. Describe how stationary waves are formed between R and S. So stationary waves, remember from our previous question, this is also a testing strategy that I do. I know that we already went over this area, an observable interference pattern. And technically we are observing because we have our detector right here, right? So let's just look back here for a refresher. We need to know that the sources are coherent, frequencies are the same, and they must overlap. Well, they all satisfy this condition, right? So if we draw like a little wave here, we can say that the wave coming back overlaps. And remember that it's coherent, right? So overlap with a phase difference of 2 pi n, which means that they're coherent. And as a result, they have the same frequency, and also they have the same amplitude. Simply because that once we emit the wave, right, it just reflects the same thing. So it's obviously going to be the same amplitude. It's just going to be the same wave. So that's that. So how D is used to show stationary waves are formed between R and S. So if we move the D detector, right, we can see that it'll record higher versus lower, versus a lower, higher, etc. So D will increase and decrease regularly based on wavelength as we move D back and forth. So for II, how the wavelength of the microwaves may be determined using the apparatus. Measure the peak. Move the D to the right until new peak is met, or the same peak, sorry, until peak with same amplitude is met, right? All right, so let's actually go back and explain why this works. So let's say our D is here, right? If we start here and we move it until we get the same value, for example, we just get this, right? And then our distance here is actually 1/2 of the lambda, which is not what we want. So to make it even easier, we're just actually gonna start at this peak here. And then we're gonna move it until we see the peak, because we know for sure that the next one is for sure gonna be lambda. So we just move it across until we reach lambda. And that's essentially how that works. Okay, so the wavelength of the microwaves is 2.8 centimeters. Calculate the frequency and gigahertz of the microwaves. So we're gonna need to know the formula of the velocity. So all waves have, I think it's this. Yeah. My teacher told me that not to memorize this, but looky, I have to memorize it anyways. So yeah, this is the velocity, right? And then our wavelength is 2.8 centimeters, which is equivalent to 0.028 meters. And remember, this is gigahertz, so it's 10 to the 9 hertz. So let's do this times 10 to the 8 meters per second is equal to F times S. Sorry, not S. Lambda. So then we know lambda is just going to be 0.028. Let's do this. And this is going to be 1.07. Let's do an extra sig fig. 10 to the 10 is equal to F. Remember that this is originally in hertz, right? And we have to convert it to the gigahertz, so we're just going to divide by 1 times 10 to the 9. And then we get 10.714. And then for the final answer, we're just going to round it to 2 sig figs. So it's going to be 11 gigahertz. A student sets up an experiment to investigate the double-slit interference of light, but finds the interference fringes observed on the screen are too close to each other to be distinguished. Which change would help the student distinguish the fringes? Okay, so this is kind of what we did before, where we have A. I know they're denoted as S, but if we have like AX over D, let's say this is our formula. This is going to be A, this is going to be X, all over D, right? This is equal to some constant. So in order to satisfy this equation, we want to increase X ultimately, right? So if we decrease the distance S from the two slits, we decrease A, that means this would eventually lead to an increase in X. And I think we just found our answer, right? Yeah. This is the opposite of what we do for the first one, so this is definitely not right. Move this screen closer to the light source. So this doesn't necessarily help distinguish the fringes. Simply because if we increase D, right, our denominator X, AX has to increase, but we don't know if our fringe will actually increase. But I'm pretty sure it doesn't because this remains constant, right? Okay, so A times X will increase, but we know that A is constant, right? A is technically a constant. So the fringes, wait. Sorry. I just realized what I did. Okay, so this is wrong. I'm just tweaking. Sorry. So it's not an increase in distance, it's a decrease in distance. No wonder this is wrong. So since there's a decrease in distance, that means there's a decrease in AX. But remember that A is constant. So then we have to ultimately decrease X, which is not what we want, right? That's opposite what we want. Use a blue filter instead of a red filter. I'm not gonna lie, I'm pretty sure this has to do with the orientation, right? But this is completely unrelated of what our equation says, let's just say. Because there's nothing about the red or the blue filter. I'm pretty sure I recall anything about the double slit experiment that affects this equation right here. So I guess we can just kind of expel that because it's completely unrelated. So ships have been damaged by water waves with large amplitudes. These waves could have been formed by adding displacements of smaller waves. Which term best describes this phenomenon? So if we say that we have a bunch of smaller waves, right? And this will eventually be called one big wave, right? I think it'd be superposition. I think that's the only one that makes sense. Diffraction is what we saw before. We just take a light source and diffract it into different areas. So it's not A. Polarization is like we have a certain source, right? And then if we reflect if we put a wave through with a certain delta, what did I just say? Theta off the center, only a certain amount of the wave will go through. And then refraction, I'm not gonna lie, I don't know what that is, but I'm pretty sure that it's somewhat related to refraction due to its root here. So we're just gonna eliminate that, and then we're thus left with superposition. I also think it's superposition because if, for example, if they're not superimposed on each other, if they're not on the same plane basically, then they don't have any reason to just add up into a larger wave, right? If they're completely unrelated, why should they add up? But since they are in the same wave, then we can say that these two are super imposed, right? All right, so for this question, the diagram shows a tuning fork above a tube of air of length 25 centimeters. A stationary wave is set up in a tube with the same frequency as a tuning fork. The lower end of the tube is sealed. This is the minimum length of tube with the lower end sealed that creates a stationary wave. Which other lengths of tube sealed at their lower ends will also create a stationary wave? Okay. So first things first, in a closed tube, I'm pretty sure that it's gonna be like lambda over 4. And it's just gonna be all multiples of this, right? So 3 pi over 4, and then 5 pi over 4, etc. Simply because if we draw this, right? Struggling with drawing. All right, so if we have like 4 lambda over 4, we essentially get a wave that ends up on pretty sure like on an antinode, or a node that is like rarefracting instead of the other one. What was it called? I forgot what it was called. Rarefraction and compression, right? So if you end up on these multiples of like 2 lambda over 4, 6 lambda over 4, these are just going to be they're going to be on different areas, which is not what we want. It's a stationary fork. It's a stationary wave, so these actually do affect the sound. So yeah, so if we look at 25, right? If we simply look at the answer choices, we can see that A, B, and C are no good. Simply because they do not satisfy the condition here. So if we have like 25, we multiply by 3, we get 75. If we multiply by 5, we get 125. So essentially, we just end up getting D, which shows the only viable thing. Almost done. All right. Water waves of wavelength lambda are diffracted as they pass through a gap of width D and a barrier. Which combinations of wavelength and gap width would produce the greatest angle of diffraction? All right, so I think we can kind of relate this to the double slit experiment, I think. This is technically a slit, right? Oh god, there's something on my monitor. All right, so if we wrote our equation, I look, just remember this, but it's wavelength, right? Which combination of wavelength and gap width would decrease greatest angle of diffraction? Angle of diffraction is based on x here, right? Basically, this means distance between fringes. So if we decrease the gap width, and increase this one, for example, we get like x is equal to d, like this, right? So we want to increase this one and decrease alpha, or not alpha, a, which is the gap width. So it's just going to be a. where we decrease this one and increase this one. Monochronic light is directed onto pairs of slits. Interference fringes that are 2.0 millimeters apart are observed on the distance. The frequency of the light is used and doubled, and the slit separation is halved. How far apart are new interference fringes? Okay, so this is still double slit experiment. So we have AX over D is equal to wavelength. So X is going to be our main distance between the interfringes, right? So it's going to be X times D lambda over A, right? So then we're going to double our frequency and half this. And we actually multiply it by 4, so it's just going to be D. A diffraction grating of n lines per unit length is placed at 90 degrees to monochronic light of wavelength lambda. What is the expression for theta? The angle to the normal to the grating at which the third order peak is observed. Okay, so I'm pretty sure it's NF is equal to D sine theta, right? Yeah, I hope so. Anyway, so N is going to be the number that we're actually looking for, the number order, which is here. And then it's going to be 3 lambda is going to be equal to D I assume it's just going to be N. Yeah. So there's N lines per unit length. D is just like here, pretty sure. And then sine theta is equal to 3 lambda over N, which is D. All right. A progressive wave transfers energy. A stationary wave does not transfer energy. State 2 other differences between progressive waves and stationary waves. Okay, so for this one, I'm gonna bring out other definitions. In progressive waves, all waves have the same amplitude. And for the second one, adjacent waves are not in phase. Sorry, adjacent particles. In progressive waves. All right, so I'm actually going to stop here. Tune into part 2 later.